All right, welcome back. So we are just starting to look at the ridge regression and how this ridge regression can be used to lower the complexity of our model, thereby avoiding the overfitting issue. So in this video, we're going to formulate the mathematics and define the objective function. What exactly is the objective function? All right, so let's take a look. So first, let's recall the objective of linear regression was to minimize the the sum squared error. Okay, so and the way we did that was using vectors and derivatives and gradient descent. Now, first of all, just kind of as a pre-processing step before we really get started, we're going to assume that our data, that our targets, okay, remember this is the targets, and I'm drawing the targets versus a feature. So we're going to think bigger than one feature, but this is all I can draw. So we're going to assume that our targets have zero mean. Zero mean. So if I make a scatter plot, there's kind of almost as much negative as there is positive, so that they have zero mean. So we're going to say that if y is our target data and it has components y1 through yn, then what we're saying here is that the mean of these guys, so the mean of y, we're going to represent with mu, is equal to 0. And if that's not true, if we go around and we collect data that has a non-zero mean, we can make it have a zero mean if we take y and from each sample we subtract the mean. Okay, so once we take y, each sample, subtract the mean, now we've got a new vector that has a zero mean. So it's like taking the z-score, except we're not dividing by the standard deviation. Okay, so that's a pre-processing step. This is called centering the data, subtracting the mean. Okay, so we're going to assume that we have zero mean. So what does that do for us? Well, if we have a zero mean data set and we're trying to fit a polynomial or a line or whatever, then we don't have to worry about the bias, the offset. We're gonna say that our line is going to go through the origin. That's because it's centered. The data is centered. Okay, so we're just not going to carry around that bias anymore. All right, now back to linear regression. And our objective was to minimize the sum squared error. So that was, we said that if the actual yi's followed this x, where x is an n by p data matrix, times theta, where theta is a p by 1 vector of weights or coefficients, then the actual data followed this linear relationship, x times theta, plus some modeling error. So this is the inaccuracies of our data, and this follows for I equals 1 to n, and then our predictions were this y hat I, and we tried to find theta, right? And so this was our predictions, right? We're just going to take x times theta. We have no error there because we're fitting exactly a line. Our predictions are exactly a line. All right, so how do we minimize the sum squared error? Well, if you remember, we set up an objective function, and that was I equals 1 to n of yi, the actual, minus the prediction squared. Okay, that's the sum squared error, the sum of the square of the error. And we could write that in vector form, y minus y hat, where y hat is the collection of all our predictions, y is the collection of all the actuals, transpose, times y minus y hat. Okay, and we worked out the gory mathematical details when we talked about linear regression, and we said we could solve this in two ways. Remember, we're trying to minimize this thing. And we could use gradient descent, or we could use ordinary least squares. And gradient descent is a little bit more involved. And so this video is about ridge regression. And so we're not going to use the more involved thing of gradient descent. We're going to use the ordinary least squares solution. So remember that the ordinary least squares solution to this, we take a derivative and we set the derivative equal to 0. And that gave us x transpose x inverse times x transpose times y. All right? I don't expect you to memorize that. There it is. Okay, great. So that was old stuff. Now what are we going to do? Well, our ridge regression. And remember, the goal, the number one goal of ridge regression is to minimize, or not minimize, but reduce the components in theta, right? This gives us a p by 1 vector, theta 1 through theta p. And in the previous video, we said that a smaller theta 1 or a smaller theta 2 or whatever, smaller components meant a lower complexity model. So what we want to do is simultaneously, have a good fit, right? Minimize the error, but we want to also encourage low complex solutions. So the way we're going to do that is with two terms. We are going to have this first term, which is the sum squared error, and we're going to have a second term. I'll explain this in a second. Okay, there it is. And we call that second term, we call that the penalty term. Penalty. Okay, so this is our objective. We're going to try to minimize this thing. And I'm going to point out that lambda is called the penalty constant, or the regularization constant. Lambda is a constant that's greater than or equal to 0. And I'm going to point out that it has nothing to do with eigenvalues or eigenvectors or anything like that. It's just the constant, and the literature usually chooses lambda as that constant. Now, the goal here then is to understand what this is, this objective is telling us. Now let's consider the extremes of lambda. So if lambda is equal to 0, lambda equals to 0, what does that do for us? Well, that wipes out the penalty completely, 0, right? And then we're just trying to minimize this first term, and that's minimizing the sum squared error. And so we know the solution to that. The solution is the OLS solution, right? And that's that tight fit, right? That's minimizing the error, the training error. So this is the highest complexity model that we can have. Okay, now on the other hand, if we let lambda be infinity, okay, and remember we're trying to minimize this thing, so infinity is, whoa, how are we going to minimize infinity? Well, yeah, that's a huge penalty to this minimization. So how do you minimize infinity? Well, you multiply it by 0. That's really the only thing you can do. So when lambda is infinity, that encourages, in this minimization problem, theta I, each component of theta, to be 0, because if each component is 0, then the sum is 0, and then we multiply by infinity, and we wipe out the infinity. So this encourages theta to be 0. That's the lowest complexity model we can have. So these are the two extremes. In reality, we choose something between 0 and infinity. And that choice is the subject of a long discussion, and we'll investigate how lambda affects the solution. So we first have to understand how lambda really affects what it is that we're doing here. So we'll investigate that in future videos, and then we'll work on how we're going to actually choose lambda. But for now, let's see if we can get a solution to this equation. Okay, and the way you do this, actually, is observe that if theta is theta 1 through theta p, then notice that theta transpose theta is this row vector theta 1 through theta p times the column vector theta 1 through theta p. And then what does that give you? Well, that gives you a 1 by p times a p by 1. That gives you a 1 by 1, a scalar. Well, what scalar is it? Theta 1 times theta 1. That's theta 1 squared. Then theta 2 times theta 2 plus theta 2 squared. Then dot, 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 theta p squared. Well, that's exactly the sum in the penalty. You see that? So we can rewrite the ridge objective function, and we can rewrite it like this. The sum squared error plus lambda times theta transpose theta. Now, the reason we do that is now we can take a vector derivative and set the derivative equal to 0. And what you get, I'm not going to go through the details because the details are very close to how we got the ordinary least squares solution. What you get is that theta, and we'll call this theta r for ridge, is equal to x transpose x plus lambda, right, because lambdas are going to affect our solution, times an identity matrix that's p-dimensional, inverse, x transpose y. Now, so we get that from derivatives. Notice if lambda is equal to 0, that wipes out the identity matrix, and we've got exactly the ordinary least squares solution. And that's what we said over here. When lambda is 0, we should have the ordinary least squares solution. Okay, so our algorithm, our ridge regression algorithm, is really not an algorithm at all. It's just a one-line calculation, okay? And we like one-line calculations, certainly, right? I mean, the ordinary least squares was a one-line calculation. All right, now, we should say that before we move on to the next video, we said that the ridge regression should convert an ordinary or an ill-conditioned problem to a well-conditioned problem. And so I do want to point out this x transpose x inverse. That x transpose x inverse in the ordinary least squares solution, sometimes that inverse does not exist. And this is kind of related to linear algebra. But that inverse will not exist when n is less than p. So that means we don't have enough examples. And this is why everybody's trying to collect your data from you, because the more examples you have, that means you can avoid this ill-conditioned problem. And the second thing that will result in this inverse not existing is when two columns or two features of x are correlated. And we haven't talked about correlation yet, but statistics is a prerequisite, so you have some notion of correlation already, like height and weight. If we used height as a feature and weight as a feature, those would be correlated, and you would see that this inverse does not exist. That's an ill-conditioned problem, and it turns out that adding this penalty term here in the ridge regression helps us convert this ill-conditioned problem where that does not exist, and this inverse will exist. So we're going to take a look at that in the next video.